right, this is going on page 42, just like yesterday. Right, Jermaine? Come on, wake it up. All right, on example 4, it says the relationship between the power output of a wind turbine and the wind speed is roughly cubic. Okay, so not perfectly cubic, but roughly cubic. An engineer collects the data on power in kilowatts generated by wind turbine against the wind speed measured in meters per second, seen above. So the data in the table can be modeled by the cubic regression. Now, on your assignment, I do ask you on some of them what you have to figure out the best one, and then you have to do it. But on the actual exam, you will be told flat out what to do, just like we are right here. Okay, and it even tells you the little generic form. Remember, we don't really care about the letters; it's where they are. But sometimes they matter. Like if it's going to ask you, we might be asked to write the equation. We might be asked what is A, B, C, and D, and then you have to write them out like that, so you know where the letters are and what they go. All right, so go to your Desmos, add your table. Oh my goodness. And type in that data. I'm going to cheat because it takes me forever up here. Thank you for sharing. What are you doing? Why nothing? All right. Once we get it typed in, do we know what kind of regression we want? Yes. We hit that little thing. Remember, your default is linear. So it's going to give you linear no matter what. So you have to change it to whatever you want, which is cubic. Now, yesterday I pointed out to you these R numbers because I just kind of want you to think about them, but that's not anything we're actually using for anything. So here, R squared is 1 because all those points are right on the curve. But on the assignment, because me saying those things yesterday, I think caused an argument in third period, because they were arguing about which one was better. And so when I went to go break up the argument, and I said, well, why do you think it's whatever? And they were like, well, because the R number was closer to 1. And I was like, no, that is not how we determine it. Like that is a true statement. But if you have to go by the data, what is the data doing? Like what we looked at yesterday, or what is the context of the problem? One of the two, or maybe the both, whatever. So I want you to kind of just see it and think about it, just because most of you will have to take some sort of statistics something in college, not necessarily a pure math statistics, but medical statistics or something that has statistics in it, even if that's not what it's called. And ours are kind of a basic thing with stats. So just kind of showing you how that all works. All right, but anyway, so there's that. This first term has a bunch of digits in it. The rest of them have 5 decimal places. You don't have to write all of them in the first one, but I do want you to write down 5. So go ahead and take what you got, which is hopefully what I got, and write down your equation. You do not round, you just write them down. Because the majority of you do not know how to round correctly, and we ain't got time for that. Thank you. I was about to ask you what's missing, and that wasn't what I was going for because I totally missed that. But what else is missing from my answer? The hat. There's no hat on my Y. This is a prediction. The Y needs a hat. Needs a hat. Okay. Easy enough. We type it in. We hit a couple buttons. Bam, there's our answer, right? Any questions? Okay. So B says, based on the model found in part A, determine the wind speed, which would result in 268 kilowatts. So I'm going to give you a minute. I want you to do that. You can discuss it with your peeps at your table. Once you are done, then check with your peeps at your table. Make sure that we all agree. Where is your computer? How did I miss this? Okay. Well, thank you for sharing. Sharing is caring. That's right. I asked y'all to compare. Why are we getting all feisty about telling each other our answers? They want to compare. Okay. Do you? You tell me. I heard some good discussions about how to use this. This is why I didn't just tell you. I wanted you to think about it. So listen, this 268, is this my output or my input? Output. And I mean, it literally said it right here. It's not always going to say it like that. But output, so that means this is y. Y equals 268. If they give me y, that means I'm looking for x, right? So in Desmos, I'm literally just going to type in y equals 268. And remember, when you hit enter, you get that slider. I think I talked about this yesterday, but I know I didn't in every class. This allows me to check different y values without having to actually plug it in or like change my numbers. But we wanted it to see, like, it doesn't really help us on this question. So then there is where they intersect. There's my answer right there. Okay, so x equals 21.65265. And what are my units? Meters per second. Meters per second. I know that for two reasons. First of all, it's up here. Second of all, it says it right here. But if it wasn't spelled out in words and you didn't know what m/s was, would that even matter? No, you just write it down. You don't have to understand it, just write it down. Also up here, it flat out tells you which is x and which is y, and that is not always going to happen. You have to have some concept of what the input is, what the output is, to make sure that you are using them correctly. Okay? Everybody good so far? We good? Okay. All right, any questions? All right, so we're done with the computers for just a second, but don't put them away. Don't close them because we're still going to use them. So just no typing until I tell you to, basically. Now we're going to look at residuals. Well, this says it's topic 2.6. We're still finishing up unit 1. But we're going to talk about them now a little bit because it all deals with regression. And that way when we get to 2.6, it's not brand new. Plus, it just makes sense to talk about it here anyway. So when we use a model to predict values, we expect our model to produce values reasonably close. That's the whole reason we use it to predict, right? But our models are not expected to result in exact values, generally, depending on the situation. Like, it makes sense. It's real world stuff. Like, it's probably not going to be exact. So what we're looking at here, what a residual is, it's the difference between the actual value and the value predicted by the model. That's your residual. Now, in stats, there's residuals and there's errors. And the difference between the two is how you subtract, which order you subtract in, which makes them very much alike and very easy to get mixed up, okay? I'm not sure why we have to talk about both, because in stats, they don't even talk about errors, but whatever. So with residuals, another reason I want to talk about it right now is I want you to remember that this was the first thing that we learned, and a residual is the actual minus the predicted. So residual equals actual minus predicted. First of all, it makes a word, wrap. Second of all, you're in an AP class, and this was the first one you learned. However, you got to remember it so you know that the residual is actual minus predicted, okay? All right. So then we have some data here, and that's what this says right here. Here's our data. And it says using the model from example 1. So this is our data that we had from the baby problem yesterday. What is the residual of the baby at 5 weeks old, and interpret the meaning of this value. All right, so my actual value, W of 5. Where am I going to find that? On the chart right here. This is the actual data. So W of 5 is 4.4. Okay. So now in Desmos, hit refresh so it'll clear everything out and give you a clean slate. Type this data back in. What kind of regression did we do for the baby problem? Linear. So go ahead and get your linear regression back. Okay. And then we want the predicted value. That's going to come from Desmos. So I'm looking for W of 5 hat. Right? That's one reason somebody asked me earlier why we need the hat. Well, we have to distinguish between the actual and the predicted. So is 5 your X or your Y? X. X. 5 is the input, it's X. So after you get your linear here, we're going to type in X equals 5 and get that line. Okay. Now for me, and sometimes it's just the board, but I don't know if if you're using it. Sometimes some of y'all don't even have a touch screen, so you have a mouse, and it probably works better. But when I try and touch this, I keep getting the actual point. So you might have to zoom in a little bit, but that's what we're looking for right there, 4.47. Okay. We good? Okay. Now our residual is our actual minus predicted. Wrap. Our actual value is 4.4. We subtract 4.47. Remember, Desmos also acts like a little computation calculator, so if you're allowed to use it so you don't make a ridiculous mistake when you add, subtract, multiply, and divide. And then this gives you negative 0.07. And what are our units here? kg. Because it's a baby. That is not the weight of the baby. Yeah, no, that would not be possible, but also not be good, I guess. All right, so we'll get to the interpretation in just a minute. But I want to go back and we want to look at this graph and I'm going to turn off my vertical line just so that it's not in my way here. And I zoomed. Let me zoom back to kind of the normal. Notice here, under where we did our regression, there's something that says residuals right here. So plotting residual is a residual plot. We don't necessarily always have to plot them, but a residual plot is something that we have to be able to look at and interpret. The way you create a residual plot is you take your predicted line, curve, whatever it is, and that line or curve flattens out and becomes a new x-axis. Okay, so it's just kind of like this, and like whoop. And then what it shows you is the distance from your actual points to your predicted points. All right, and you can tell right here, like this third one, it's the farthest away, right? I think we can all agree with that. And they all kind of look semi-close, like whatever, right? So when I hit plot, and then it's very unexciting because I can't see anything. So then I hit the little magnifying glass, and now you see how I have the line. My x-axis, my line became my new x-axis. These are the points on either side of the line. My x values are exactly the same as what they were. The y values are the residuals. Okay, and if we look at them together, I think I can do it. The residuals themselves. Yeah, I don't know why. Well, I don't know how to change E, I'm not gonna lie. But I can change these by changing, oh, no, I can change it right here. Well, I can turn it on and off. You can change them here, maybe. Yeah, there you go. That's where you can change them. Oh, no, no, no. There we go. Undo, undo, undo is my friend. So do you see how when I have it zoomed like this, and I know it might be hard to see the bottom, but you can do that yourself. What I did was I zoomed in on E, and then I zoomed back. Then I zoomed back on the regression. And then now it's like the same scale. So you see how the line just kind of laid down and became the x-axis? But then if I zoom in on the residuals, I see them a little bit better. So when we get to 2.6 and we're looking specifically just at residual plots, they're going to look like this. So understanding that the x-axis that we have now is the function can help you wrap your mind around whether things are overestimates or underestimates. Clearly here, these 2 points are above the line. These 3 are below the line, right? The line is the prediction. So for when it predicted for these 2, it is an underestimate because the prediction is under these points. For these 3, the line is over it, so it is an overestimate. Does that make sense to you? Okay, when you look at 5, if I click on this right there, that's our negative 0.07 because that's the distance from the line. It's negative, but the prediction is an overestimate. Does that make sense to you? And because we're saying overestimate with negative, I see where that can get mixed up. That's why you want to think about, or even if you're just looking at it like this, okay, that, you know, clearly this is under it so that, and we can't, you know, if we had to explain it, we wouldn't say it's under it because it's under the line. We would say, you know, or it's really it's an overestimate because the point's under the line. We can't say that. We'd say it's an overestimate because my residual is negative, something like that if I had to explain it in like, not, you can't say because look at the graph, that's what's happening. It doesn't work that way. But think about what's happening there. So since this is negative, even if I didn't have all this to look at, since this is negative, I do have this to look at. And so this is where the 5 is, and this is the line. The line is over the point. That is an overestimate. Okay? It doesn't ask us to explain here. We just have to interpret it. So we can say the model is an overestimate. Is it always an overestimate? No. It's an overestimate of actual values of actual value of t equals 5 weeks. Okay, so, and that's all we've proven with our little, by actually doing this. This is all we really figured out. I mean, we can look at the graph and talk about the other ones, but we can't make a general statement about it always being an overestimate. I had a question last period, which was very good, which, do we have to spell out the word weeks? No, we don't. You can abbreviate all day long. Totally fine. I know your English teachers probably hate it, but this ain't English, so it's fine. As long as your abbreviations are either a generally accepted abbreviation or something that totally makes sense. Sometimes some of y'all make up your own abbreviations that make absolutely no sense. Be careful with that, okay? Any questions at all? Awesome.